The last type of damped system we'll look at is the overdamped system, which happens when our damping ratio is greater than 1, which means that the roots of that characteristic equation are real but unique. When this is our situation, we have free vibration and an overdamped system, then our total solution is going to look like this for x of t. So notice that we have two exponential functions here with different exponents. We will have two unknown amplitudes, but like with the critically damped system, there's no trig functions. There's no sine, there's no cosine, so we're not going to expect any oscillations. We just have two functions that are going to be decaying. And if we notice, we're going to see here that both of them have basically this negative exponent that is going to only get more negative as t gets larger. So given enough time, both of these exponentials are going to die out, and we're going to find that x of t is eventually going to go to 0. Now, the C1 and the C2 we'll need to find once again by using initial conditions. So these are what we find for those amplitudes on the exponential functions. Now, how do we get to that closed form solution? For the overdamped system, it's going to be a little bit more roundabout than we saw for the critically damped and the underdamped system. But again, let's presume that we've already solved the roots of our characteristic equation, and they look like this. And we already know it's overdamped, so we know that zeta is going to be greater than 1. So we know that we have real repeated roots. Now, I'm going to rewrite this. It's going to maybe not make too much sense at the moment, but in this version of my proof, I am going to say I'm going to take that plus or minus part. Now, this part is real. We know that because zeta is greater than 1, so we're taking the square root of a positive number this time. But I'm going to rewrite this. Let's say here I have omega n square root zeta squared minus 1. Now, it doesn't, I want it to look like the form I've been working with, where I'm going to have my lambda in the form of a plus or minus j times b. And this is, I know what the expansion of this looks like for the solution to my ODE, but right now I don't have a j term. But what I can do is I am going to take this, I want a j so it looks like what I had before. Right? But now I've multiplied this second part by the square root of negative 1. Well, that's not good. I've changed it. What if I multiply it by another j? So I've multiplied it by square root of negative 1, square root of negative 1. I multiply those together, and I get negative 1. So I can also multiply it by a negative out in front. So effectively, by multiplying it by negative j times j, I'm multiplying that second piece of this by 1, and I haven't changed it. But now, it is in a form that works with my lambda equals a plus or minus b times j. Now it's in the form that I can work with because I have my a term here. So the coefficient in front of this j term is going to be a little bit tricky here, but I'm going to call this whole thing, let's just say capital B, and I'll call this thing little b. So without the j, it'll be the little b, and that will include this negative sign. So I'll actually move that to here. So little b will include that. So my solution to my second order ODE, where I know the characteristic of roots, is going to be in the form of, I'll just write e to the at on the outside, c1 cosine. Now, in this form, it's capital B times j, which I'll replace in a second here, plus c2 sine of capital B times j. And I want to rewrite this now and split up capital B, cosine of little b times j, and these have t's with them, plus c2 sine of little b times j times t. All right, so it does look a little bit different than what we had before, because we're going to have now a j term inside the cosine and inside the sine term. But we know from calculus 2 how we can handle something like that, because in Calculus 2, we were taking trig functions of imaginary terms, and now we have the cosine of a purely imaginary term and the sine of a purely imaginary term. So we can break this up. The cosine of b times j times t, well, I'm taking the cosine of an imaginary term. That is going to be the hyperbolic cosine, or the cosh function, which I'm going to write out here in its longer form. I can write it as exponentials. So it's going to be e to the negative b times t plus e to the b times t over 2. And here I have the sine of an imaginary function, which is going to give me a hyperbolic cosine, but I can rewrite this also as exponentials, e to the negative bt plus, this will be minus, e to the bt, and that's over 2 times j. I can do some algebra now, and I'm going to get a c1 over 2 e to the a plus b times t when I multiply exponentials together, plus a c1 over 2 e to the a minus b times t, plus I will get here a c2j over 2 e to the a plus b times t, and actually a minus ctj over 2 e to the a minus b times t. So I skipped a little bit of the steps here, but I'm getting rid of the j from this denominator, and I'm expanding out my like terms. The algebra isn't too important. I am going to be, again, doing a little bit of hand waving in the setup of this just to show what we have. All right, so what do we have here? I have an e to the a plus b t term. I have 2 of those, and an e to the a minus b times t term. I have 2 of those. So I'm actually going to factor that out. So I have a c1 over 2 plus a c2 over j over 2 e to the a plus b times t, plus I have a c1 over 2 minus a c2j over 2 e to the a minus b times t. All right, so I have some coefficient in front of my a plus b term, some coefficient in front of my a minus b term. Since I don't know c1 or c2 yet, I'm going to get those from the initial conditions. I can actually just rename this whole thing c1 and this whole thing c2. So I'm just going to simplify it and solve it this way. So I'm just renaming c1 and c2 for convenience. Because I don't know what they are yet, before I do, I'll just redefine them this way. So this is c2 e to the a minus b times t. And finally, I can put this together with the things that I knew from above of how I defined a and how I defined b. Right, so a was negative zeta omega n plus, and then my b. Here I included the negative sign, so I have omega n times root of zeta squared minus 1. And there's also an omega n attached to that. And that's times t plus c2 e to the a negative zeta omega n minus a negative omega n square root of zeta squared minus 1 times t. All right, so a little bit roundabout in how I got here. There's certainly easier ways to get here, but we see that this is the same closed form solution that we saw on the slide, where we have 2 exponential terms. We have that negative zeta omega n plus or minus omega n times the square root of zeta squared minus 1 times t. And then I will still have these 2 coefficients, c1 and c2, that I'm going to need to use my initial conditions to solve for. I'm not going to solve for them here, though. But going back to our slides, we see here the solutions for our c1 and c2, with a simplified proof of getting to x of t.